It's my great pleasure to have Pedram Hekmati here, all the way from Auckland. He's the unique visitor, really, as part of our New Zealand International Visitors Program. And he will tell us about, well, he will explain to us what a see, I can't even say it. So I will learn how to pronounce this and find out what it is. Thank you.
Thank you so much, Stephen. Yeah, it's a great to be in Sydney. This is my first international trip in 2 years. This is, when I was asked to give a what is seminar, I was quite keen to talk about something that I'm trying to learn myself. So I'm by no means expert on the subject, but I should know enough to hopefully answer your questions. And then I usually read the what is notices in the, well, the what is articles in the AMS notices. So hopefully this is going to be a sort of overview of the subject, and I will give you references for more sort of technical details when needed. So I was also informed that it's a quite mixed, potentially mixed audience. So I will start quite gently with just recalling some of the classical invariants in algebraic topology. Say a few words about their usefulness and also some of the shortcomings, and then use that sort of as a springboard to motivate the definition of TQFT, a topological quantum field theory, and a cohomological field theory is sort of an enhancement of the topological field theory. All right, so the first invariant you learn in algebraic topology is the Euler characteristic. And originally this was defined for polyhedral surfaces. So if sigma is a polyhedral surface, meaning it's a convex hull of finitely many points, not all in the same plane, then the Euler characteristic is simply counting the number of vertices minus the number of edges plus number of faces. And this definition was used to classify, for instance, Platonic solids. And now in the modern language, we think of this as sort of cells of a finite CW complex. So that's the modern viewpoint on these on vertices, edges, and faces. So we can think of these cells as generating vector spaces, and then we can write these things as the dimension of alternating some of the dimensions of these vector spaces. So in this case, R goes from 0 to 2. So Ci is, so for instance, C0 is a vector space generated by the vertices of a polyhedron. And you can actually show that there's a very natural notion of boundary between these vector spaces. So you get what's called a chain complex. And by the Euler Poincare principle, you can also write this as an alternating sum dimensions of the homology groups. So. All right. And what's nice with this perspective is that now we can think of this as computing dimensions, the Betty numbers of a cochain complex, and it extends now beyond 2 dimensions. So this is, I feel like, the modern definition of Euler characteristic. And also what we see here is that this is really computing dimension of something a bit more richer, which has more information, namely the homology group. So I feel like there's in modern language, there's a categorification of Euler characteristics, which is homology. And homology is associated to every topological space. Well, in general, I should be down here. An abelian group, and it's also structure preserving. So if you have continuous maps between topological spaces, you get homomorphism between the groups. And you can show that this is a homotopy invariant. So homology has, so this is a covariant functor, and its homology is a homotopy invariant. And it's additive with respect to disjoint union. So if you take 2 topological spaces, take the disjoint union, then the homology groups add up. All right, so this is going to be important because when we get to TQFTs, essentially what TQFT is a sort of a multiplicative version of homology. And a consequence of this is that if you think of the empty set as a topological space, then the homology valid on the empty set is 0. And now the question is, what can we do with this invariant in terms of classifying topological spaces? So in topology, we're really interested in classifying things up to homeomorphism. So let's just do it dimension by dimension. In 2 dimensions, homology, or really the Euler characteristic, is the complete invariant. And in fact, in dimensions 3 and lower, classification of the homeomorphism or piecewise linear equivalence or diffeomorphism all the same. So this is really a complete classification of, say, the diffeomorphism closed surfaces. So the Euler characteristics of the Riemann surface, a closed oriented Riemann surface of genus G, is given by the formula 2 minus 2G, and G here is the number of holes in your Riemann surface. And this can be extended to allow for boundary components, marked points, and also if you matter is unoriented, you can also include that into the classification. All right, so homology seems to be the only invariant you need to understand surfaces up to homeomorphism. And what if we go up to 3 dimensions? So before doing that, let me say that another classical invariant is the fundamental group. All right, so again, this is, I'm assuming everyone's done basic topology, so I give a very quick definition. So if you have a topological space, you pick a base point, so just fix a point in the space. Then this is space of loops based at x0, and then you identify loops if one loop can be contracted continuously to another, so up to homotopy. Okay, so that's your intuition behind fundamental group. And if you go to 3 dimensions, we'll continue. Then it turns out that the fundamental group actually determines homology completely. So the fundamental group is the basic invariant with which you want to try to classify 3 manifolds. And now you have to be careful. In 3 dimensions, homotopy equivalence is not the same as homeomorphism, but you still have homomorphism and diffeomorphism classification still are the same. And here, this is a much wilder world, 3 manifolds. So there are some very powerful results that we can use to try to understand 3 manifolds. So if you, again, restrict our attention to closed orientable 3 manifolds, we have the prime decomposition, which tells us that any such manifold decomposes into finitely many oriented prime 3 manifolds. So, and again, so assuming things are oriented, this is a unique decomposition up to homeomorphism. So really, to understand 3 manifold up to homeomorphism or diffeomorphism is enough to understand prime manifolds, and oriented prime 3 manifolds are either have an infinite cyclic group, so this is the only such 3 manifold, or they're what's called irreducible. And irreducible means that any embedded 2-sphere bounds a ball inside a 3 manifold. All right, so since we know what the non-irreducible one is, we really need to understand the irreducible 3 manifolds. And now, if things was easy, the fundamental group will do the job, and it almost does. Okay, so now it turns out that due to the geometrization theorem, Thurston's geometrization, I guess, theorem now, the classification by the fundamental group is almost complete. So the fundamental group classifies all irreducible. Again, assuming everything is closed oriented. 3 manifolds, except what's called the lens spaces. So this follows by the fact that you have this what's called J decomposition of irreducible 3 manifolds, and the hyperbolic ones are classified by rigidity theorems, Mostar rigidity, and the Hawken manifolds are classified by Waldhausen previously. And the Seifert fiber 3 manifolds are also classified by the fundamental group, except the lens spaces. So I'm gradually working up to why we need something beyond these classical invariants. So very quickly, say a few words about the lens space. So if you have 2 integers p and q coprime, the lens space is a quotient by a free action of Zp, the cyclic group of the 3-sphere by the cyclic group. So the fundamental group of the lens space is Zp. It turns out that this is, in fact, one of the problems with classifying lens spaces using fundamental group, because it doesn't see the Q fundamental group. So it turns out, for instance, if you pick P equals 7, Q equals 1, this is homotopic, equivalent to L72, but not homeomorphic or diffeomorphic.
Pedram, you didn't say where Q comes in.
Yeah, I'm trying to save time here. I'm not right. Okay, let me define the LP. So LPQ, if you think of the 3 spheres sitting inside C2, it's Z1, Z2 in C2. So it's the unit ball inside C2, and then we quotient out by ZP action, which identifies Z1, Z2 with, so you have the action by the roots of unity 2 pi I on P, and then here is where the Q comes in. So it's the ratio of Q with P, X on Z2. Yes. So they have the same homotopic groups because it's the Z7. And the first homology is also a abelianization of the fundamental groups. It's the same in this case. The second homology is 0, and all the other higher homologies vanish, and all the higher homotopic groups are the same as the spheres. So these classical invariants don't suffice to classify lens space after homeomorphism. Not even up to homotopic equivalence, actually. So for the homotopic equivalence, you need something called a torsion linking form. And for homomorphism, you need this invariant I wanted to get to, which is the Reidemeister torsion. So Reidemeister, this actually predates TQFTs. Reidemeister introduced or R torsion. Introduce an invariant that can actually classify lens spaces up to homeomorphism. And so this was in 1935. It was generalized by a student to higher dimensional lens spaces. And the Reidemeister torsion, essentially what you need an extra piece of data, which is a representation of the fundamental group of the lens space. So with this extra data, U1. So the way you pick this representation is send the 1 to some element, root of unity, which is non-zero, not equal to 1. Right? You don't want a trivial representation. And the idea of introducing this representation is you want to kill off the homology completely, right? So you introduce this local system defined by this representation, so that the chain complex becomes cyclic. And so essentially the only information is in the 0th degree homology, and the torsion that just becomes a real number. Okay, so I think if I remember, the formula should be PQ. So this representation is that's the Reidemeister torsion is 1 minus x. So it's a positive real number, and R is a reciprocal of Q. So that's where the Q comes in. Mod P. Okay, so as you vary these representations, you can actually show that this gives you a classification. So these are homomorphic exactly when homomorphic Q tilde exactly when Q equals Q tilde plus minus 1, again mod P. Okay, all right, so it turns out now if you want to classify three-dimensional manifolds, we need something beyond the classical invariance and the randomized torsion, at least in 3 dimensions. That's the job. And then what is R torsion? In fact, much later, there's a paper by Schwartz, I think it's 1978. It shows that this R torsion can be obtained as a partition function, so a particular TQFT. So R torsion is a TQFT invariant. And by this I mean that there's a particular functional you can define, such as evaluated on the 3 manifold gives you the R torsion, and the functional is in this case is a Gaussian, it's a quadratic functional. But physicists call it a path integral, and the action is called BF theory, right? Or in modern language, abelian Chern-Simons theory. But the point is that this is connecting now to these ideas that developed mostly during the 80s, that there are new invariants of, especially in low dimension topology, can be obtained from ideas from physics. And what's exciting about this is that while these other invariants in algebraic topology are homotopy invariants, these TQFT invariants tend to be much finer invariants. So for instance, the randomized torsion is a homomorphism invariant. And it gets even more dramatic when you go to 4 dimensions, where the classification of the homomorphism and diffeomorphism are not the same. And as most of you know, the Donaldson theory gives you smooth invariants. So the Donaldson polynomials are invariants of the diffeomorphism class of the 4 manifold. The topological classification, at least for closed, simply connected 4 manifolds, was achieved by Friedman. So, but any such topological 4 manifold could meet many inequivalent smooth structures. Okay, so this was supposed to be a short, somewhat short introduction to invariance coming from TQFT. So let me now say a few words about what a TQFT is, and then cohomological field theory is an enhancement of a TQFT, which is again motivated from ideas in physics, namely what's called topological string theories. All right, so now let me move on to say a few words about what a TQFT is. Okay, so the idea is with a TQFT is that it's supposed to be defined using something else. Remember, homology was defined as a functor from a category of topological spaces into, say, for instance, abelian groups. And it's an additive functor with respect to disjoint union. So the idea of a TQFT is to replace the domain of this functor by what's called a bordism category. So there's a natural equivalence relation between closed oriented manifolds, namely bordism. So we say that 2 and 1 and 2 closed oriented manifolds are cobordant if they form the boundary of a manifold of 1 dimension higher. So if so if the disjoint union is the boundary of a manifold of 1 dimension higher, and you can show that this satisfies the relations for an equivalence relation. So it defines a bordism set a priori, but you can show that under Cartesian product disjoint union is a bordism ring, and it can be extended to generalized cohomology theory. So this is the bordism of a point. And now what you can do is, as well with this information is to build a category, the bordism category. Board n, where you put the objects to be exactly n minus 1 closed. Again, smooth oriented closed n-1 dimensional manifolds. And now instead of taking, in topological space, we have just continuous maps between them. The morphism in the bordism category should be equivalence class of bordisms up to diffeomorphisms that preserve the relative to the boundary. So bordisms, which would be n-dimensional manifolds, modulo diffeomorphisms relative to the boundary. And this category has, well, there's a natural composition of bordisms, namely just gluing. So this is sort of, again, going back to the classical invariants, gluing here would simply be excision. You have the Eilenberg-Steenrod axioms tell you they can excite a piece of manifold, and there's exact sequence connecting the homology groups. And similarly, we want our whatever functor we're going to define, which is our TQFT, to be controlled by bordisms. And then you can glue two bordisms together to form another manifold whose boundary are manifolds one dimension lower. And you can also introduce sort of a monoidal structure on this, which is just taking this joint union of objects, manifolds, and the bordism. And you can show that this joint union is, of course, symmetric under the swapping. So this is what's called a symmetric monoidal category with this additional structure. And there's another such category sitting around, namely the category of vector spaces with the linear maps and tensor product as the monoidal structure. So a TQFT in this very sort of nicely packaged form would be a functor from the bordism category, preserving the product to the category of vector spaces over some field. Well, you can replace it by modules over a ring and tensor product. Okay, so this is a functor and preserving so it's a symmetric monoidal functor. Functor. So if you unpack this, this means in particular that if you take the disjoint union, then it should send this of objects, you should send this to vector spaces and the tensor product of these vector spaces. X and Y as objects. So already you see that, for instance, the Euler characteristic would not be a bordism invariant, because, for instance, the two-sphere is null cobordant to the empty set just by the empty ball, it's boundary of a ball. Yeah, do you have a question? Yeah.
The audience has focus points. Maybe you should step off.
Oh, I'm blocking the. Got it. Oops. Is this working? I can read. Yeah. So. Okay. Good. Yeah. So it's just board N has objects n-1 dimension closed oriented manifolds, and the morphisms are bordisms between. Okay. So, and also another property of this multiplicative nature of this functor is that if you evaluate it on the empty manifold, it's instead of being 0, it gives you the field. Okay, so in this sense, you can think of this as a exponentiated version of homology. And in 2 dimensions, this functors can be classified in a very simple way using what's called an algebraic structure called Fabinus algebra. So the theorem is that any such functor up to equivalence is the same. Let's write like that. Or in bijective correspondence with commutative. Fabinus algebras. And this is not just a sketch of the proof. It's not too hard to see, because the reason you have this nice classification is because the bordism category, board 2, has a very nice presentation. So obviously, the objects should be one-dimensional closed manifolds. So these will be generated by, you have this empty set, you have the circle, and you have the disjoint union of circles. Okay, so this is what the objects would look like. And the morphisms, well, it would be Riemann surfaces with boundary circles. That's the bordism in this category. And it turns out that these kind of bordisms are using Morse theory. You can show that all such surfaces can be cut up into it's called pair of pans, copans, the cap, which is the bordism from the circle into empty set, and the co-cap. And since these are symmetric, you also need this relation, which tells you how to swap two circles. Okay, and then some relations. So essentially, the idea is that if you apply your functor to these generators and relations, Z of a circle gives you a vector space, and then applying Z to morphism should give you a linear transformation. So if you have two circles going in, that gives you the tensor product from a map from a tensor product of two vector spaces into a vector space, which is just a multiplication. And so you have a vector space equipped with a multiplication, co-multiplication, unit, a co-unit. So this is called, you have a structure of an algebra and a co-algebra. And now you can impose another compatibility on these structures, and that comes from the relations, which I didn't write down. The main relation is called the Fabinus relation, which tells you that the data of this is a commutative associative ring with non-degenerate bilinear form on it. Okay, so the data would be this, the underlying vector space associated to the circle. You have a multiplication, and then you can show that the information of the Fabinus relation is equivalent to having a bilinear form or a trace map. That's non-degenerate. Okay. Okay, so this is quite abstract, the definition. Of course, to bring this to life, you want to construct some concrete examples. So we know that if you have a finite dimensional commutative Fabinus algebra, you should be able to construct a TQFT. Let me just mention this before moving on to cohomological field theories. One easy example is that we all doing first year group theory is PQV to be the group algebra of a finite group, and took invariant functions, so under conjugation, so the center of your group algebra. You have a convolution product here, and then you have a very natural trace form, which sends a function to its value at the unit element, and then we normalize by the order of the group. Okay, so it's a little exercise to check that this data is a commutative Fabinus algebra, so it defines a two-dimensional TQFT. And the way you usually construct TQFT is to count something. So the TQFT in this case is counting local systems on your surface and on the boundaries. So the vector space V should be the space of functions, complex valued functions on the set of local systems on the objects, which are circles, say. So not to do the circle case, because all the other ones you get by tensor product into C. And local systems, in this case, your group is finite. Local systems are just G covers, Galois covers, or principal G bundles, if you like, up to isomorphism. These are just classified by up to iso. This is what this is. These are just classified by representations of pi of the base into G up to conjugation. So this is the same as conjugacy classes in G. Because you just look at the image of one that determines the homomorphism. So this tells you that these are functions on G mod G conjugacy classes, which is exactly a G invariant function. So count the local systems on the objects in this case, and take functions that gives us the correct vector space. And then obviously I don't have time to go all through all the details. If you also count local systems on this bordisms subject to the boundary conditions, that's going to give you what the value of this functories on bordisms, and it's between, say, n one ingoing circles and 2 outgoing circles. I'm add them up to n here. And if you evaluate this on a closed Riemann surface, no ingoing and no outgoing boundaries, you can think of a closed Riemann surface as a cobordism between the empty set and the empty set. So then this is just counting the all the local systems, but the measure we use is we mod out by the automorphisms of the local system. So this is okay, and this is again it's a little exercise to show that this is just counting the volume of the character variety. And now using the fact that this is a TQFT, we can also chop up by surface into pieces and then work out what this functor looks like if you decompose the surface into pieces, and then you get this famous Fabinus formula. Okay, so this is, I just want to mention this because it's a very nice little application of this particular TQFT. All right, and then finally, let me say something about what is a cohomological field theory. So as I said, the way you usually construct these TQFTs is to count something. And in topological string theory, you're interested in counting the J-holomorphic curves into symplectic, compact symplectic manifold. And unlike this example here, these typically produce invariants not just valued in this vector space, but valued in characteristic classes of surface bundles. So, the example I'm thinking of is Gromov-Witten theory. So Gromov-Witten theory is an example of the topological string theory that requires sort of an enhancement of this, and the enhancement is exactly what the cohomological sort of is. Abstraction is what is a cohomological field theory. So, a cohomological field theory, in a nutshell, is a parameterized version of a TQFT. I think I've answered the question. What is so family's version of the TQFT. So the idea here is that we have some fibration over a base where the fiber is a surface. And we want to construct, again, one of these TQFT-like functors that when you apply it to this surface bundle, it gives you a cohomology class in the cohomology of the base. And it should vary in a way that makes sense, meaning it shouldn't be continuous dependent on the base, but only sort of cohomologically. So we want to get homotopy invariance out of this. And now another property this should satisfy is, okay, so this should give you some cohomology classes in the base. And another thing this should satisfy is that it should be natural with respect to base change. So with respect to base change, so if you have a continuous map from B to B tilde, then Z applied to families of a B tilde should be related to Z applied to the original fibration. And what this tells us is that this functorially means that it's sufficient to work out this functor on the universal example, because all the other surface bundles are obtained by pulling back. So what is a universal bundle for a surface bundle? This is a classified up to isomorphism by maps from the base into classifying space of the diffeomorphisms, maybe orientation preserving diffeomorphisms. And this space has a very nice realization as the moduli space of curves. This is MG, I didn't say, but if you can allow for marked points on your surface, it's MGN. And if you also, what we're interested in is stable curves. So these are curves that are possibly nodal. So some parts can shrink to a point. in the surface, and they should only have finite order morphisms. So if you allow for stable Riemann surfaces or complex curves, then what you get is the Deligne-Mumford compactification of the moduli space of curves. So if we, yes, let's do this. Okay, so it means that we really want to work out the Z on this universal case. So there's a universal stable curve over MGN. So I'm assuming since we want the stable curves, I'm assuming that 2G minus 2 plus N is greater than 0. And then let's call these tensors omega Gn. These will be elements in the cohomology of the moduli space of curves. Okay, so this is the basic output of a cohomological field theory, and now this moduli space is the boundary of the moduli space contains nodal curves. So you want to also impose some factorization conditions on these tensors when you're restricted to the boundary. So the additional information of cohomological field theory is how these tensors behave with respect to some swing conditions, or gluing maps. And these axioms are, of course, modeled on the properties of Gromov-Witten invariance. So the Gromov-Witten invariance gives you the most studied example of a cohomological field theory. There's another example, namely called the Verlinde cohomological field theory, which is a family's version of the usual Verlinde TQFT, if you're familiar with this. Okay, I am. So this is a good point, because this is the part I didn't want to do, is to write down the full axioms of a cohomological field theory. So let me refer you to the there's some natural maps. I'll wrap up in 1 minute. Between the moduli spaces, MGNs. So for instance, you can forget a marked point that gives you a map from MGN to MGN minus 1, and then some other maps belonging to the boundary of the Deligne-Mumford moduli space. And so these omega GNs need to satisfy some factorization condition with respect to these maps. And there's no shortage of references for learning about these axioms, but there's a beautiful survey of the topic by Pandey Pandey in his ICM talk in 2017. So I refer you to Pandey Pandey 2017 ICM talk. He not only gives the axioms of the theory, but he also gives 3 very nice examples where you can see how this theory comes to life. All right, so hopefully everyone knows what the cohomological field theory is now. Questions? Yeah, so the idea with the marked points is that, I guess from a TQFT point of view, you can think of them as very tiny circles, and these are supposed to be in and outgoing circles, like strings, if you think of it from topological string theory. That's I guess the motivation for physics for including marked points. So you're asking if you have 2 different inequivalent surface bundles over B. I don't see, just from the axioms, I don't see what it is there's nothing in the axioms that would tell me anything about the relation between them. Because when you do that, you see, the way I've written it now is sort of just part of what this family's version of the TQFT should satisfy. But once you do it in the universal case, you're using some factorization conditions that are very specific to MGN and the sort of the local structure of the boundary. So if you now move away from MGN and just take 2 different bundles, I don't see, so over any base, I don't see why those factorization would tell you any particular relation. So I would say I don't think so, but yeah. Maybe I can also say somehow I didn't get to any concrete examples, but one way of getting these kind of tensors is to look at certain vector bundles over MGN. I mean, this is typically how these characteristic classes, these cohomological field theories are constructed. So obviously, there's always what's called a Hodge bundle over MGN. So over each curve, you take the cotangent bundle of the Riemann surface. Another bundle you can get is what's called the Fellinde bundle, which comes from the space of non-abelian theta functions. So the fiber over each curve is the sections, holomorphic sections of a line bundle of the space of flat connections or local systems over that curve. And as you vary these are what called conformal blocks, and that gives you a vector bundle of conformal blocks. And there's a way you can use modular functors to produce these kind of vector bundles. So you use VOAs to produce modular functors, and then there's a prescription how you can go from modular functor to a vector bundle of MGN. And once you have one of these, you take a characteristic class like the Chern character of this bundle, and that typically gives you one of these cohomological field theories. So the characteristic Chern class, the Chern character of these bundles are one way of producing these tensors.
Okay, well, thanks again for very nice talk.